Today we're delighted to have Robert Young, who will speak about geometry and topology at many scales.
Thanks. It's great to be here again. So, what I want to talk about is basically non-smooth geometry and topology. I want to talk about maps and surfaces and objects that have structure at many different scales. And the thing with non-smooth geometry is, there are often very good reasons to approximate something by a smooth object. And even a lot of things in nature are almost smooth. Even if you take the Earth, you rescale the Earth to the size of a billiard ball, it's about the same smoothness as a billiard ball. And things that are smooth are often a lot easier to work with. Like if you have that sphere, I mean, it's a lot easier to describe a sphere in terms of a center and a radius, 4 numbers, compared to describing the Earth takes a couple volumes of mass. Or if you have a piece of paper, if I have a flat piece of paper, I can describe this in terms of the coordinates of the 4 vertices, but now not so much. Regardless, though, if we unfold this, you notice that the creases are a relatively small proportion of the area of the piece of paper. The piece of paper is still mostly flat. And there's theory behind that. I mean, you can think of the piece of paper as essentially a map, Lipschitz map, a distance decreasing map from a rectangle to R3. And then you have Rademacher's theorem that says that any map like that is differentiable almost everywhere, which matches the way that your piece of paper is creased along, maybe a graph or at least something about one-dimensional, something of measure 0. And so what I want to do today is I want to talk about things like this, things around this. I want to talk about functions that have structure at many scales, and on one hand, what weird things that we can construct with functions like that, and on the other hand, if we have some mild conditions on these functions, a Lipschitz condition or a condition on area or volume, what does that tell us about the function? How can we then restrict these functions? So let me start. Quick recap of what it means to be a Lipschitz function. Function is Lipschitz if it's a map from one metric space to another metric space that doesn't increase distances by too much. The distance between f of x1 and f of x2 is less than or equal to L times the distance between x1 and x2 for any pair of points x1 and x2 in your space. And these are very common in metric geometry because often, if you're dealing with metric spaces, the metric is the only structure you have, and so a map that preserves that metric is about the best you could hope for. But also, it behaves, it affects measure and dimension in a nice, straightforward way, in the sense that if you have a domain with a bound on the Hausdorff dimension, then the Hausdorff dimension of the image is smaller than the Hausdorff measure of the domain, or Hausdorff dimension of the domain. And the Hausdorff measure of the image scales according to the dimension and the Lipschitz constant. It multiplies the volume of a set by some constant. And the other thing that I want to remind you about with Lipschitz maps is the theorem of Rademacher, which says that a Lipschitz function from Rm to Rn is differentiable almost everywhere. So like I said, what I want to talk about today is what weird stuff you can construct under this condition, and on the other hand, what you can do with this condition to limit the weirdness of the stuff you construct. So let me start with the first one. What weird stuff can you construct under this condition? I have 2 examples I want to show you. First is a construction of Kaufman, where he constructed rank 1 maps from the cube to the square, and one is a family of topologically non-trivial low-rank maps. And these are basically. So let me start with this example of Kaufman. Kaufman constructed an example of a Lipschitz map F from the cube to the square, which is surjective. The image is the whole square, and the rank the rank of the derivative is at most 1 almost everywhere. So at almost every point, it should collapse a neighborhood of that point to something one-dimensional. Now, if this were sorry, there's a bit of lag. Okay, oops. Okay. So this is impossible for smooth maps. Sart's theorem tells you that's impossible for smooth maps because if you have a smooth map where the derivative has rank at most 1 everywhere, then every point is a critical point. Every point in the image of that map is a critical value, and Sart's theorem tells you that the set of critical values has measure 0. So the image of the map has measure 0. So there's no way you can cover the square with a set of measure 0, but you can construct a non-smooth map. You can construct a self-similar map that does exactly that. So let me show you how this works. Okay. So what do we want to do? We want to construct a map from a cube to a square, which is Lipschitz. The derivative has rank 1 almost everywhere, and it's surjective. So let's name these. Let's call this Q for cube, and let's call this D for the disk. And what we're going to do is we're going to construct something self-similar. So we're going to cut Q into a grid, into a 4 by 4 by 4 grid. So sides length 1/4, and we're going to cut the square into an 8 by 8 grid. Side length 1/8. Right. So inside of each of these, because we've got 64 cubes with side length 1/4 on the left side. We've got 64 squares of side length 1/8 on the right side. Inside each of these cubes of side length 1/4, I'm going to construct a smaller cube of side length 1/8. Let's name those cubes. Let's call them Q1 up to Q64. These are little cubes of side length 1/8. And let's name these squares, these 64 squares, D1 up to D64. These are squares of side length also 1/8. Right? And for each of these, I'm going to mark the center point and call those centers P1 up to P64 are the centers. Right. Now, I'm going to construct a map basically one scale at a time. So for the first step of this step in the construction is to construct a map on F on the whole cube minus the union of the little cubes, so that the boundary of the big cube goes to the, let's label this center here, let's call that P. The boundary of the big cube is P. The boundary of all the little cubes go to the corresponding center of the corresponding square. And we're also going to ask that F is Lipschitz. So for instance, the derivative of F is bounded, and all the derivatives, the image of F is one-dimensional. It's a graph. And this is not too hard to do. We can draw a graph that contains all of these points. Just connect P to each of the centers in this grid. Make a big star-shaped graph there. And it's straightforward to construct a continuous map, even a Lipschitz map, that sends the boundary of the big cube to the center of the square and sends the boundary of each of the little cubes to the center of one of the little squares. Right? And so once we do that, we can construct the rest of F by rescaling. Right? The next step would be to construct F on one of these little cubes. And so to construct it on one of those little cubes, we basically do a rescaling of the original procedure. We cut the little cube into 64 smaller cubes. We cut the little square into 64 smaller squares. Inside of each of these cubes, we inscribe another tiny cube. And then we could redefine a map on the small cube minus the tiny cubes. Since the boundary of the small cube, well, we were already sending that to the center of the small square. And since the boundary of all the tiny cubes to the center of one of these tiny squares. And the image lies in this little star-shaped graph, rescaled by a factor of 8. Right? And so we can do that in all the 64 small squares, or all the 64 small cubes. And then each of those small cubes is going to contain 64 more tiny cubes, and we can do it in each of those tiny cubes, and so on and so forth. In the end, what we end up with, well, first, because the side length on the left and the side length on the right is the same, when we do this rescaling, when we rescale the domain by a factor of 8, we just rescale the range by a factor of 8, the Lipschitz constant, the derivative stays the same. So we maintain the same bound on the derivative. And so in particular, the result is Lipschitz with the same Lipschitz constant as the original. And the result has a derivative which is rank 1 almost everywhere. And it's defined everywhere except, well, what's left when we go from the big cube to these 64 smaller cubes to these, even more tiny cubes and so on and so forth. What's left out of this construction, the only thing that's left out is a Cantor set. And so we can extend by continuity to extend it over that Cantor set. And then the result contains the big graph, the smaller graphs, all the smaller and smaller copies of this graph, and it contains the closure of all those graphs. So it contains the closure of all these center points, which is the entire grid, or which is the entire square. So what we end up with is a map that sends the cube to the square surjectively, where the derivative is never bigger than rank 1. Is this okay so far? So this is there's a certain amount of flexibility to this construction. I've given this for a map from the cube to the square, but if you wanted to, you could change the domain, you could change the range, you could change the tree you use here. But there is one limitation here, which is that all the maps that you can construct this way are sort of topologically trivial. You can show that if you have a simply connected M and a Lipschitz map like this, where the rank of the map is at most 1 almost everywhere, then the image is kind of in a tree. I mean, you can sort of see the tree in this picture. We have this star-shaped graph for connecting the center of the big square to the centers of all the small squares, and then connecting the small squares to the tiny squares, and so forth, so on and so forth. The map factors through a tree. And the reason for that is basically that even though Sard's theorem doesn't quite work here, Sard's theorem doesn't work for Lipschitz maps, Stokes' theorem does. If I have a Lipschitz map like this from some simply connected space to some to some Rn, where the derivative has rank 1 almost everywhere, then in particular, if I take any closed curve in the domain, there's some disk whose boundary is that closed curve, and then this rank 1 map sends that disk to something of area 0. And what does it mean to send it to what possible? So what does that mean for the closed curve? What is a closed curve that has area 0? Well, if you have a closed curve with area 0, that means that it's kind of it's tree-shaped. Every time it goes over an edge, it has to then go back over that edge. Any time it goes out, it has to come back. And so you can combine. So any closed curve maps to a tree like this, and you can extend that to say that in fact the entire domain maps to a tree like this, and so your map is topologically trivial. It is whatever your domain, whatever your range is, your map is going to be homotopic to a point. Okay, so far?
What is an R tree?
If you look at this, you notice that the edges are getting smaller and smaller. An R tree is so we want to allow for that. So the technical definition is that an R tree is a It is a metric space where there is a unique arc connecting any 2 points. It's a metric space that has no loops in it. And so that includes things like, you have a vertex and then infinitely many edges coming off of it, or, you have an edge and there are lots and lots and lots of edges coming off of it, more than this. But yeah, it's a generalization of a tree to a metric space setting. Questions?
A simply connected manifold, is it a smooth like a Riemannian manifold, or like what is the underlying structure that you're assuming that it has?
I think so. So certainly Riemannian or smooth is enough. If you have less than that, well, you have to have enough structure to define a Lipschitz map. So let's say Riemannian or smooth. Okay. Questions? So rank 1, all these maps collapse. So what about higher ranks? It turns out in higher ranks, so the image of very close curve has area 0. What happens in higher ranks? It turns out in higher ranks you can construct examples that are topologically non-trivial. So let me say that a Lipschitz map has co-rank 1 if the derivative is never surjective. If the derivative always has rank at most 1 less than the dimension of the target. So the derivative is never surjective. Again, if you have a smooth map like this, so let me stand here. So if k is greater than or equal to 4, then you can construct a Lipschitz co-rank 1 map from the k+1 sphere to the k sphere, which is not non-homotopic. Again, this is impossible in the smooth case because of Sar's theorem. This is impossible in the smooth case because if you have a smooth map where the derivative is never surjective, then Sar's theorem tells you that the image has measure 0. And so if you have a map from sk+1 to sk where the image is not all of sk, then it's no homotopic because you can delete a point from sk to get rk, and then any map to rk is no homotopic. So how do you prove this? What does this construction look like? It follows from a slightly more general, it follows from the following lemma, that if alpha is any map from Sm to Sn, with m greater than n, then the suspension of alpha extends to a co-rank map from the m+2 disk to the n+2 disk. So let me just briefly remind you what a suspension is. The idea of a suspension is, the idea of the suspension is that you have some space x, and you construct the suspension of x by adding a north pole and a south pole, and then a line segment from every point in x to the north pole, and a line segment from every point on x to the south pole. In particular, if you apply this to a sphere, if you apply this to the equator, well, you can think of the globe, a sphere, as the equator plus the north pole plus the south pole plus a line segment from any point on the equator to the north pole and from any point on the equator to the south pole. And in general, if you have an n sphere, the suspension of an n sphere is an n+1 sphere. You can construct you can take a circle and you can add lines, a north pole and a south pole with lines to make it into a 2-sphere. You can take a 2-sphere, treat it as the equator of a 3-sphere, and construct the 3-sphere as a bunch of the north pole, a south pole, and a bunch of lines from the equator to the north and south. If you have a map between 2 spheres, I have if you have a map between 2 spheres, if you have here's my sphere Sm, here's my sphere Sn. If I have a map between 2 spheres, then I can construct a map between the suspensions of those spheres, essentially using those coordinates. So my original map maybe sends some point x to some point alpha x over here. The suspension consists of the North Pole plus the South Pole plus lines from the North Pole to the South Pole through every point in the equator. And so a natural thing to do is to take that line from the North Pole to the South Pole through x and send it to a line from the North Pole to the South Pole through alpha of x. Basically, we send what's written here. The suspension of alpha sends x comma t to alpha x comma t. So the North Pole goes to the North Pole, South Pole goes to the South Pole, the equator goes to the equator, and then everything else, we want to make sure that lines from the North Pole to the South Pole through the equator go to lines from the North Pole to the South Pole through the equator. So we want to show this extension result, that if you have map alpha between two spheres where the domain has bigger dimension than the target, then the suspension extends to a co-rank 1 map, one of these weird self-similar maps. So how do we do this? Let me do this on this board. The basic idea is going to be very similar. I want to construct a map from a disk, let's call it dn plus 2, to a disk dimension dn plus 2. Actually, to make this match the previous construction, let me draw this like the previous construction too. So let's visualize, we have a cube on the left side, and then we have a square on the right side. Again, we want to divide the cube up into a grid. We want to divide the square into a grid. Because of the dimension mismatch, we can do that. We can break this into a k by k grid. We can break this into an L by L grid. Because of the dimension mismatch, we can choose k and L such that on one hand, if we look at k to the m plus 2, the number of cells over here, this should be greater than L to the n plus 2, the number of cells over here. And furthermore, we want L to be bigger than k. We want L to be at least 2k. Or wait, sorry, other way around. We want k to be bigger than L. We want these to be smaller so that we can fit things in here. So we want L to be bigger than k. If we do that, then just like before, these squares all have length 1 over L. These cubes all have length 1 over k. If L is a lot bigger than k, if L is greater than 2k, then that means that inside each of these 1 over L by 1 over L cubes, we can draw a smaller cube, which is 1 over L on the side. And furthermore, because of our choice of k and L, we have more little cubes over here than we have squares over here. So let's let n be the number of squares. Let's n equal L to the n plus 2. And let's label n of those cubes, q1 up to qn, cubes of side 1 over L on the left. And let's label these squares d1 up to dn squares of side 1 over L on the right. And then try to do the same thing that we did over there. Try to construct a map F on Q minus the cubes that we can rescale to construct the whole map that we want. So let's let F on the big cube minus all the little cubes to D. What do we want? Well, we want the boundary to be the suspension of alpha, so that F restrict to the boundary of Q is the suspension of alpha. And then in order to do this rescaling construction, we're going to want the restriction of the map to the boundary of one of these small cubes to be essentially the same thing. we want f restrict to the boundary of qi to be a rescaling of q to the alpha. The rescaling of sigma alpha. Now, there's a topological obstruction here. This isn't always possible. We can't always take a map like this from the boundary of a square, the boundary of our of dm plus 2 to the boundary of dn plus 2, and then break it down into a bunch of these little maps. But here we can. Here, because of our hypothesis, because we're assuming that alpha is because we're taking the suspension of alpha, there's a nice trick that lets us do this. I heard this trick from Goldstein, Eyewash, Anka. There's a nice trick that lets us do this, which is, well, let's take our cube minus a bunch of little cubes. Let's take our square, which has been subdivided into a grid. This cube minus a bunch of little cubes, this is homeomorphic to a ball minus a bunch of little balls. And I can line all those balls up along a diameter of the ball. Likewise, this square, this skeleton here is, well, it's not homeomorphic, but there is certainly a map from, if I take a disk minus a bunch of little disks, there's certainly a map like this. And so if I want to construct a map that sends this to this, and sends the boundary of the cube to the boundary of the square by sigma alpha, and it sends each of these little cubes to the boundary of one of these little squares by the map sigma alpha, it's enough to construct a map from here to here that sends the boundary of the ball to the boundary of the disk, and sends the boundary of each of these little balls to the boundary of each of these little disks by sigma alpha, or by a rescaling of sigma alpha. And that's easy to construct because what we can do is we can give this cylindrical coordinates let's call our coordinates, a radius, an angle, and a height. And we can give this cylindrical coordinates a radius, an angle, and a height. And then we can define a map that sends a point, rho theta z, to rho alpha theta z. Right? We can define a map that sends the equator of our ball to the equator of our disk by alpha, and it sends the North Pole to the North Pole, it sends the South Pole to the South Pole, and it sends any line through the equator to a line from the North Pole to the South Pole through the equator by exactly this formula. Furthermore, the same thing applies to each of these little balls and little disks. It's going to send the North Pole of this little ball to the North and South poles of this, and same for all these others. It's going to send the equator of this to the equator of this. It's going to send send lines from the North Pole to South Pole to lines to the North Pole to South Pole. This map sends the boundary of the big cube to the boundary of the disk by the suspension of alpha, and sends the boundary of qi to the boundary of di by a rescaling of the suspension of alpha. And furthermore, the image of this is the n-1 skeleton of the image, and so it has rank n-1. It has co-rank 1, like we want. Okay. Once we have that, then the rest is exactly as before. Once we have that, then this is exactly what we need to then repeat the process. Our original map sent the boundary of the big disk to the boundary of the boundary of the big square by sigma alpha, and it sends the boundaries of all the little balls to the boundaries of the little squares by rescaling of sigma alpha. And so we can take a copy of that original map and plug it in each of these little cubes. Just like before, we can draw a bunch. We can break all these little cubes into smaller grids. We can break all these little squares into smaller grids, and we can repeat the process at a smaller scale. Because of the way we chose our cubes and we chose our squares, they have the same side length, 1 over L, 1 over L. So when we do that rescaling, it rescales the domain by a factor of L, it rescales the range by a factor of L, and so the Lipschitz constant stays bounded. And so we can extend by rescaling as before to get a map which is Lipschitz, corank 1 map, which is sigma alpha on the boundary. So again, we can construct. This is impossible for a smooth map because a smooth map with corank 1 couldn't have surjective image. The image couldn't be all of dn plus 2.
Can I ask a question about, so is it before you were mapping onto a graph, so a one-dimensional thing, is the place where you're only getting to corank 1, that upward pointing arrow there?
Yeah.
Where you're just, so those are, it's the interface, it's a codimension 1 thing that you're aiming for.
Yeah, so we are aiming for we take a in our target space, we're looking at this L by L grid. We're taking the boundaries of all the cubes in that L by L grid, so it's the n-1 skeleton of that grid.
So the outside of those balls collapses onto the codimension 1.
Exactly. So the map from here to here is basically we rearrange all these balls into a grid, and then we blow up all the balls so that everything else collapses to the grid. Okay. So once you've done that, you're nearly done. Because if you have a corank 1 map like this that restricts to the suspension of alpha on its boundary, you can take 2 copies of those. Think of it as the left half of the sphere and the right half of the sphere. You can take 2 copies of those, glue them together to get a map from Sm plus 2 to Sn plus 2, which still has corank 1. And because of the way you constructed it, because it's sigma alpha along the interface, it's the double suspension of alpha, sigma squared alpha on the whole thing. And then you can conclude that for any alpha from Sm to Sn with m greater than n, the double suspension of alpha is homotopic to corank map. And the smallest non-trivial case where this happens is if you take the double suspension of the Haupt vibration. Haupt vibration sends S3 to S2. The double suspension of the Haupt vibration sends S5 to S4.
When you say that it's the smallest non-trivial case, you mean it's the smallest non-trivial case that follows from the theorem, right? For example, does the Haupt map have a representative itself?
You can show, and this is some work of Larry Guth, you can show that you can't do this for the Haupt, you can't do this for the single suspension of Haupt. So this is really the smallest case where this can happen at all. So yeah, okay. So you can do this sort of self-similar construction where you take a big map and break it down into smaller pieces and then smaller pieces and smaller pieces. And if you are careful about the scalings that are involved, the final result is Lipschitz. How does this work? Like, what is the trick we're playing here? The trick really comes from carefully reading what I said on that first slide. I said on the first slide that a Lipschitz function f from Rm to Rn is differentiable almost everywhere. It's differentiable off of a measure 0 set. But that's measure zero in the dimension. That's measure zero in the measure on the domain. So that's measures. That's a set that has m volume 0. These constructions, for instance, Kaufman's construction, is a map which fails to be differentiable on a Cantor set, which has measure 0, but has dimension between 2 and 3. Depending on how exactly you set it up, you can arrange for it to have dimension very arbitrarily close to 3. And so what we're doing here, the trick we're playing here, is we're taking that Cantor set, which has dimension bigger than 2, and Lipschitz condition implies that the Hausdorff dimension of the image of a set is less than or equal to the Hausdorff dimension of the original set. If we have a set with dimension bigger than or equal to 2, then it can certainly map to a set with dimension exactly 2. And so one way of thinking about the trick we're playing here is that there are Lipschitz functions that are differentiable almost everywhere, but that almost everywhere doesn't really help you that much when there is a drop in dimension like this. Because you can have a set of dimension 2.5, which has measure 0, and then you can have a Lipschitz map that sends that measure 0 set to surjectively to the square. And there are a bunch of other ways of taking advantage of this. I've shown you like these two examples here, but there are a bunch of other ways of taking advantage of this. If you have a dimension drop like this, that you can construct weird self-similar maps. Berdnikov, Guth, and Manin used this to construct, or used a similar construction to construct maps between what they call scalable spaces. Goldstein and Heiwash used a construction related to this to construct orientation preserving homeomorphisms with orientation reversing derivatives. It's very clever. It involves a picture like this where you have one grid and then you have another grid and then you take the squares in one grid and you permute the squares to turn the whole thing upside down, and then repeat that at many scales. It's a weird construction. And then I use this with Stefan Wenger to construct Holder parameterizations of the Heisenberg group, maps from R3 to the Heisenberg group. It can't be Lipschitz because of the dimension condition, but you can construct maps like that that are 2/3 minus epsilon Holder, which is just about the limit of the. Is this okay so far? Okay. So this is the half of the talk where we say talk about how weird Lipschitz maps can be. But there's also something going on here that's this is specifically saying that these can be this weird where there is this dimension drop. So the converse ought to be that when there is not a dimension drop, then we can avoid all these phenomena. So how does that? So what can we say about that? On the other hand, if you've just gone through half the talk saying, okay, here's how bad, here's how weird you can construct a Lipschitz map, but really, how bad can they actually be? If we have dimension the same dimension, if we have the domain and range the same dimension, how bad can they actually be? It turns out they can. That in that case they're a lot better behaved. So. How bad can a Lipschitz function be? Well, let's try to construct something. Let's try to construct, what is the worst Lipschitz function that you can construct from, say, R to R? And because there's a range of functions you can construct from R to R, this is probably too rough. I mean, it's not a Lipschitz function. The derivative is too large. The derivative is too large, and the derivative of a Lipschitz function has to be bounded. This is probably too smooth. I mean, it looks not quite C2, but very close to C2. You really ought to have corners in the worst Lipschitz function. Ooh, that's a lot. Sorry. Yeah. Okay. So we're really looking for something about like this, where we have roughly bounded derivative, but that derivative can change very quickly. You ought to have points. So if this is kind of the worst Lipschitz function, exactly how weird, exactly how far from smooth is this? And there are ways to answer this. There are ways to answer this based on what's called quantitative differentiability. And one way to look at this is to try to analyze graphs of Lipschitz functions like this. Try to analyze these graphs. So let's define, say we have a Lipschitz function f from R to R. Let's define gamma f, call it gamma to be its graph. Then the coordinates of gamma are Lipschitz, so gamma itself is also Lipschitz. And then we can approximate the length of gamma by formulas like this. So for any I, we define Li, this is the ith approximation of the length of gamma, to be the sum from j equals 0 to 2 to the I minus 1 of the distance between gamma of j plus 1 times 2 to the minus I minus gamma j to the minus I. The idea is basically that we're taking our curve. Say our original curve was defined on the interval from 0 to 1. And then we're subdividing. We're taking here's the subdivision into 2 parts, here's the subdivision into 4 parts, 8 parts, and so on. Every time we do this, every time we subdivide, the length of the curve increases. And so L1, so these approximations ought to form a non-decreasing sequence. On the other hand, this sequence of approximations is bounded because gamma itself is a Lipschitz curve. Gamma itself has bounded length, and so these approximations should form a bounded monotone sequence. First year calculus tells you that that converges. And so in particular, for any epsilon greater than 0, we should be able to find some n sufficiently large so that if we take the nth approximation and the nth plus 10th approximation, there should be very little difference. But what does that mean if you can take your curve, if you take the curve on one of these segments and the length of that one segment is just about the same as if you subdivide your curve into 1,000 tiny pieces and connect those pieces? It means that every point in that subdivision has to be pretty close to the curve you started with. Because if there's some point in the subdivision that's way out here, then the subdivision at best goes like this, and the length of that subdivision is going to be a substantial chunk bigger than the length of what you started with. And so, if n is sufficiently large, then the n plus 10th subdivision is really close to the nth subdivision. In fact, you can quantify this. So the way I've set this up, you have to be a little bit careful because if you're looking at L sub I, if you're looking at L sub n, you're not just looking at one interval. You're looking at every interval along this curve, and so you can't necessarily say something about every interval. But on 99% of those intervals, gamma is root epsilon close to a line. And this is not exactly Rademacher's theorem, but it's very close. It tells you that on a large chunk of your curve at very small scales, your function is very close to linear. Like I said, this is not quite Rademacher's theorem. Rademacher's theorem tells you differentiability almost everywhere. This tells you, it's kind of close to a line at 99% of the 99% of the curve. But the advantage of this is that this is a very quantitative argument. So same notation as before. Let's let gamma be this graph. Just like we talked about just like we talked about the lengths, we can talk about just these approximations. Gamma sub I is the ith approximation, and then L sub I is the length of gamma sub I, and because of this property, because every time we subdivide, it increases the length. we know that the difference in length, the difference L sub I plus 1 minus L sub I, that's always going to be greater than or equal to 0. And as I goes to infinity, the L sub I should converge to the total length of gamma. And so we should be able to write the length of gamma as a sum of these differences L sub I plus 1 minus L sub I. If we try to construct a complicated curve, if we try to take a curve and we add a bump to that curve, what happens to the L sub i's? Well, if we start with a nice smooth curve and then we add a bump, there's going to be some scale, there's going to be some interval where when we subdivide to form that bump, it increases the length by some definite amount. So every time we add a bump to our curve, one of these differences, Li plus 1 minus Li, increases. And so, in a sense, the complexity of gamma is bounded by its length. A curve which is bumpy everywhere at every scale would have to be infinitely long. And since this is this is only finite length, there has to be some limits to this. There have to be some limits to how bumpy your curve can be, how bumpy your function can be at how many different scales and how many different places. And you can quantify this. There's a nice version of this inequality due to Doric-Soro, which is also true for Lipschitz functions from Rm to Rn. That's getting a little bit past, well, certainly past the time we have left. So for functions, we can do this. What about surfaces? Can we quantify, in some sense, the topology of a surface? Can we quantify how complicated a surface is? Can we answer the question, what is the least smooth or the most complex surface in Rn? Now, there are obvious problems with this question. Here are some problems. It's pretty, here we have the Menger sponge. You could easily argue this has infinite complexity. Here we have, I'm thinking of this surface as sort of an infinite tiling of R3. So this surface extends out to infinity in all directions. And again, the only reasonable answer to how complex is this is sort of infinite. And so let's try to exclude these questions. Let's try to say that we want to look at the least smooth, most complex surface with a given area. Because if we restrict the area, if we force the area to be finite, it excludes these possibilities. Another problem with this question is that it is very subjective. You need to make a decision for yourself. You can pretty reasonably conclude that the simplest surface, the square or flat square ought to be a pretty simple surface. But then you have to ask, okay, well, what's a little bit more complex? Say we add a handle to this square. That's probably more complex than just the square. And well, maybe you argue that if you have like a little handle and a big square, then that really shouldn't be very different from the original square. But at some point, you then have to say, okay, now if I take my little take a square and I just tile it with a lot of little handles like this, you need to make some decision about, okay, how many little handles does it take to count for one big handle? You really want to quantify this. So there is some subjectivity here. But let me propose one measure, not least reason why, because I can prove something about this. But let me propose one measure, which is that that I can give you a way to quantify how non-orientable something is. If I have d less than n and k is a d cycle with coefficients in z mod 2, so for instance, a closed, non-orientable or non-oriented d-dimensional surface in Rn. What does it mean to be orientable? Well, one definition of orientability would be as if I can take that cycle with coefficients in z mod 2 and replace and turn it into a cycle with coefficients in the integers with exactly the same support. An orientation of the Klein-Bottle would be exactly that. It would be a way of representing the Klein-Bottle as a cycle with coefficients in z. The Klein-Bottle is not orientable, but we can construct a sort of orientation, a pseudo-orientation of the Klein-Bottle. we can construct an integral cycle P, which is congruent to K mod 2 at the expense that we have to add to the area of the Klein bottle. Specifically, what we add, the Klein bottle is you take a cylinder and you glue the ends with a twist. If you cut that cylinder, or if you cut that Klein bottle, you get the same cylinder again. And so you can take that cylinder if you close up the ends. If you put a disc on either end, you get a cylinder with two ends, the sphere. Sphere is orientable, and then let's just glue that back together again. Because of the twist, your ends don't cancel out. So what you end up with is the Klein bottle plus two copies of that disc you cut along. Two copies of, well, in this picture, this disc here. And so you can, so how can you measure non-orientability? Maybe it's the amount of stuff you need to add in order to get a pseudo-orientation like this. Maybe it's the amount of stuff, maybe it's the amount of cutting that you need to do in order to get something orientable out of it. So let's try to find that. So in this case, the area of the pseudo-orientation is the area of the Klein bottle plus those two discs. The area of the Klein, for any D cycle A, we can define the non-orientability to be the minimum area of one of these pseudo-orientations. I want to be more formal about it, but I don't think we have time for that. If your cycle is orientable, then the non-orientability is just the area. Otherwise, this is additive. The non-orientability of the sum is at most the non-orientability of the pieces. And then you can ask, now that you can quantify this, what's the surface where the ratio of the non-orientability to the area is largest? And it turns out that, well, and
I didn't understand what you meant by a sum. Is that a connected sum? What is A plus B?
Oh, because I'm thinking of these as cycles.
Oh,
So
cycle.
yeah, so the sum as cycles, adding up the coefficients. So where is this largest? I can't quite tell you that, but okay, I don't have time for this. But it turns out that it is in fact that this ratio is in fact bounded for any surface. The non-orientability is bounded by a constant times the area. Basically, because just like we can take a Lipschitz function and describe it in terms of bumps and claim that every time we add a bump, it adds some extra area, we can do the same thing for a surface. If you take some very complicated surface with, maybe a big handle here and a bunch of little handles here, and add some non-orientability, maybe all these handles are glued in with a twist, so maybe these are all cross handles. If I take a surface with a lot of non-orientability due to a lot of different handles like this, how can I bound the non-orientability in terms of the area? Well, one way to think about it is that every time I added a handle like this, it added a little bit of non-orientability, but it also added a little bit of area. So every step in this construction adds to the non-orientability, adds to the area. If you can show that those additions are of the same order, then that gives you a way to bound the non-orientability in terms of the order of the area. And I claim we can do that. We can decompose any mod 2 cycle into simple pieces, basically by a greedy algorithm. What you can do is you can take a surface like this, you can find a region where it's a little bit more complicated than it could be, where you can find a region where there's a way of taking that surface and making it a little less area by squashing out some of the complexity. And then repeat that. You keep on finding regions where you can squash out a little bit of complexity, reduce the area a little bit, reduce the non-orientability a little bit. In the end, what that gives you is it gives you a way of writing your surface as your original piece plus a bunch of little simple pieces as your original surface plus a bunch of handles of various sizes. And if you can bound if you can bound the complexity of all those pieces, then you can use the additivity to bound the complexity of the whole thing. Okay, that's a lot faster than I wanted to do that, but I'm out of time.
So let's suppose we had a geometric space. You know, maybe we can take it to be homeomorphic to some manifold or whatever. Can you say anything about Lipschitz functions on that? Like, do any of your theorems apply if you don't have like an underlying smooth structure?
Well, okay, so there one thing you can do. Okay, so it all depends on what you want to do. But one thing you can do is, so Rademacher's theorem tells you that if you have a Lipschitz function on a line, then it's differentiable almost everywhere. One thing you can do is that if you have a space that's made up of lines, in the very basic case, you have the plane. You can draw a whole bunch of parallel lines in the plane in all sorts of different directions, and then you can ask, okay, if you have a function which is differentiable along every one of these lines, or differentiable or close to a line, or in this quantitative sense, close to a line on 99% of these lines, then what does that imply for your whole function? Well, for Rademacher's theorem, it implies that your whole function is differentiable in the multivariable sense. It has a gradient. But you can apply this in other spaces too. If you have the Heisenberg group, for instance, you can foliate it by horizontal lines in different directions that don't commute. And then you can apply differentiability along those lines to give you some differentiability theorems for the Heisenberg group. And this is Ponceau's differentiability theorem.
Earlier you said, if I recall correctly, that like with Kaufman's construction, that like the set of points where it's not differentiable, I think you said it's how differentiable to be arbitrarily close to 3. Is it possible to make it so it's exactly 3?
Oh no, well, okay, so Mariana would know this. I don't know it off the top of my head.
Yes.
Okay. Yes.
Okay.
So in the very end, introduced the notion of non-orientability as a measure of how complex surface is. But like the examples you drew on the board seem to me orientable.
Yeah. So what I'm thinking about is say I draw a cube say I draw a 3 cube in R4.
Yeah.
Right. Then what I can do when I say glue on a cross handle, I mean cut out 2 discs and take a cylinder and glue on one end, twist it, and then glue on the other end. That's what I mean by a cross handle. So yeah.
Yes.
Reminder that next week the colloquium is half an hour later and in Ryerson 251.